Welcome to the lecture 18th of course Polymer Science and Technology. In today's lecture, we will see the equilibrium step polymerization reaction. So, this step polymerization reaction can proceed in two types of system. One is the closed system, another one is the open system. As we know or we have learned in the previous classes that in case of step polymerization or polycondensation reactions, some small molecules such as water or HCl, they are liberating as a condensation product, and they should be removed from the polymerization system. So if they are not removed at all, means your system is closed, whatever product and whatever byproduct is producing, it is present inside the reactor only, and no byproduct is removed from the reactor, then this type of system is known as the closed system. Okay, closed system means no removal of product or byproduct during the polymerization reaction. Okay, in case of open system, removal of product or byproduct is possible, and this may yield to high molecular weight of polymer. So let us see the closed system first. We will take the example of polyester, diacid and diol. They are reacting together to form polyester and water as a byproduct. Okay, although there are many steps involved in this polymerization reaction, but we will not consider the intermediate steps. We will write only the final step, means diacid and diol, they are reacting to form polyester, and rate of polymerization K1 and K2, they are the forward and backward rate of reaction or rate of polymerization reaction. Here let us consider that the M concentration M naught is the concentration of the carboxylic group and hydroxyl group initially taken. PM naught is the concentration of polyester COO and H2O at equilibrium, and M naught minus PM naught is the concentration of the carboxylic and hydroxyl group at equilibrium. Okay, so at equilibrium we note that the rate of forward reaction is equal to rate of the backward reaction, and we can write as K1COOH OH is equal to K2COO H2O. Okay, this is a forward rate constant multiplied by the concentration of the reactant diacid and diol is equal to K2, which is the backward rate reaction backward rate constant multiplied by the concentration of the product and byproduct, which is a polyester resin and water. So at equilibrium we can define the equilibrium constant capital K as a ratio of forward and backward rate constant. So this ratio K1 over K2 will be ratio of the concentration of the polyester, water, over the concentration of the reactant carboxylic or diacid or diol, carboxyl group or hydroxyl group, or we can say diacid or diol. So here we can write COO as P concentration M naught. In place of H2O we can also write P M naught, and in place of COOH and OH we can write this expression in terms of generalized concentration of monomer. So this is going to be P concentration M naught whole square divided by within bracket M naught minus P M naught whole square. So if you take out the M naught as the a common m naught will be cancelled out, and this will be p square over 1 minus p whole square. And we know that the 1 minus p, 1 over 1 minus p is nothing but xn bar. So it will be square of the xn bar multiplied by p square, where p is the conversion I have already explained. So xn bar, which is the number average degree of polymerization, will be equal to under root k, k is the equilibrium rate constant, under root k over p. Okay, so this is another relationship for xn bar relating the equilibrium rate constant and conversion. At very high conversion, where conversion is almost 100%, or we can say the value of the conversion is just about 1, so this expression will be xn bar is equal to under root times k. Okay, so let's say in order to obtain a moderate molecular weight of polymer or polyester, say xn bar 100 is our target. So in order to obtain 100 xn bar, the value of the equilibrium rate constant must be 10,000, and this value is very high, very large requirement, and usually it is not possible in case of polyesterification reaction. Polyesterification reaction, the value of equilibrium rate constant may be as high as 10 or near 10. So the requirement of 10,000 is almost 1,000 times higher requirement. Okay. However, in case of polyamides, the value of equilibrium rate constant may be as high as 1000. But in case of polyesterification, the value of equilibrium rate constant is near 10. Therefore, in case of closed system, the molecular weight is very less. You can see if k is 10, then xn bar or number average degree of polymerization is just, you can say 3 something, 3 means the polymer which is forming due to the polyesterification reaction of diacid and diol will contain, each and every chain will contain just 3 or 4 units. So you know that if the number of repeating unit is less than 10, we will not call the polymer as polymer. It will be termed as oligomer. Oligomers means just few units. Okay, so we can see, we can say that in case of closed system, we are not capable of forming polyester of sufficient molecular weight. We will be just getting a viscous liquid of having oligomers containing 3 or 4 repeating units. That's it. So in nutshell, in case of closed system, molecular weight is very less. We will not obtain a polymer. We will be just getting oligomer. Now let us see in case of open driven system, what is the condition. In case of open driven system, diacid and diol are reacting, rate constant are K1 and K2. Polymer, which is a polyester, is forming, and byproduct water is forming. But in case of open driven system, we will continuously remove the water from the reactor so that the concentration of the product will decrease, and in order to compensate, there will be more conversion in forward rate constant, means more and more reactants reactant will react together to form the product, because we are continuously removing one of the product or byproduct from the system. So we are basically shifting this equilibrium towards the product side, and in our product side polymer is our desired product, so it is our aim or target to shift the equilibrium towards the product side. This is the usual technique to increase the yield of the desired product. So for high molecular weight, the byproduct water should be, the concentration of the water should be very low. This is called shifting of equilibrium in forward or product direction. Okay. So at equilibrium, again we can say K1 concentration of the carboxylic group multiplied by the concentration of the hydroxyl group is equal to backward rate constant multiplied by the concentration of polyester multiplied by the concentration of the byproduct, which is water. Rate of polymerization is controlled by the rate of water removal from the system, because the quickly we will remove the water from our reactor, equilibrium will shift towards the product direction and more product will form. So we can say the rate of polymerization is dependent upon the rate of water removal from the reactor. Now equilibrium rate constant, we know capital K is ratio of forward rate constant to our backward rate constant, and this is concentration of the polyester multiplied by the concentration of the water over the concentration of the reactants, means carboxylic group and hydroxyl group. And we can write in place of concentration of the polyester resin, we can write Pm naught, and we are not converting this water in terms of generalized monomer term M and P, we are leaving it as it is. Over in place of concentration of the carboxylic and hydroxyl group, we can write this generalized equation. So here M naught and this square will cancel out and we'll get equation P, concentration of the water, over M naught 1 minus P whole square. Okay, and this 1 minus P, 1 over 1 minus P whole square can be written as Xn bar square. So it will be Xn bar square P times H2O concentration over the concentration of monomer initially taken. Okay. Again simplifying it, instead of P we can write Xn bar minus 1 over Xn bar. So here the term of square will cancel out with the Xn bar, and our final equation will be Xn bar within bracket Xn bar minus 1 concentration of the water divided by the concentration of monomer initially taken. So we can shift the other term so that the concentration of the monomer is concentration of the water is on the left hand side, and then rest of the equation is Km naught over Xn bar 1 within bracket Xn bar minus 1. So here we can notice that the Xn bar square, if we will multiply this Xn with this Xn bar, so Xn bar square is inversely proportional to concentration of the water. That's mean for high value of the molecular weight or number and degree of polymerization Xn bar, the concentration of the byproduct water should be very very low. Okay. Okay, so this is the end of lecture 18, and I hope you have understood this and enjoyed it. Thank you very much for your patient hearing.